Good morning. Hello, everyone.
Good morning.
Hello.
Hello.
Can you hear me?
Yes.
I can't hear you.
You can hear us.
Okay, better. Yes, I can hear you now. Great. Let's wait for a few more minutes and we'll start.
Вкусно, блядь. Вкусно, нахуй. Еще раз пробуй.
Okay, great. Welcome once again. So today is probably our final lecture on second order curves. We will consider their equations in polar coordinates, something what we started last time. Then we'll have a few more words about a hyperbola. Uh, Not as much detail as about the ellipse, but we'll still have some considerations about it. And then we'll study the general topic of how to reduce a very general second order curve to the canonical form. And that will be done. So then the next lecture next week will be about three-dimensional second order surfaces. So whereas now we're studying second order curves in 2 dimensions, that will be about second order surfaces in 3 dimensions. So one more dimension, which are important for, as we'll later see, uh, problems like function optimization. It is very important to understand the geometric shape of such curves. And then the remaining 3 lectures, I think, will be devoted to a crown jewel of our course, as I promised, the Keplerian orbital motion, which will bring together our analysis of second order curves and three-dimensional coordinate transforms. So all will come together in a very exciting astronomical and physical problem, which will have direct practical consequences. Okay, so today we're completing our study of second order curves. So you remember what we started doing last time? We started deriving equations for second order curve for the ellipse in that case in polar coordinates. All right. So, oh, ellipse in polar coordinates. Why is it important? First of all, because the orbital motion problems will require it. And secondly, because we'll see that in polar coordinates, the equations for the ellipse, parabola, and hyperbola are very similar to each other and can be very easily extended from one to another. So this provides some kind of unified view, which is very, very useful. So you remember what we did. We started with a classical ellipse, x squared over a squared plus y squared over b squared equal to 1. And in this case, the origin of our coordinate system xy coincides with the center of the ellipse, right? Coincides with the center of the ellipse, that's the center. But that's not exactly what we want. We want an equation in polar coordinates where the origin coincides with the focus rather than the center. So that's our focus F1. We put a new coordinate system. You remember we did it. So this is, let's say, eta. This is the xi axis. So actually the eta coordinates of any point is the same. But there is a translation, a shift between xi and x. And you remember we said that the distance between the center and the focus. What is the distance between the center and the focus of the ellipse?
Is square root of a square minus b square.
Square root, you say, of a squared minus b squared. Okay, or if we expand it, because b squared is a squared times 1 minus eccentricity squared, if you remember, then this is exactly the square root of a squared minus e squared 1 minus e squared. Therefore, a squared cancels, and we have simply ae. This is very useful to remember. This is just ae. Yes, you are right. But that's, in general, what you said is absolutely correct. So, our coordinate transform are in the following. The new coordinate xi is x minus ae. When in the original coordinate system, x is ae, so we're in the focus, then xi is equal to 0. Okay. And the eta coordinates are the same. Whatever point we get, its projection to both axes is the same. So eta is, eta is y. Or obviously x is psi plus ae, eta is y. Substituting this into our equation, we get, well, let's make immediately the next step. And now in these psi eta coordinates, we'll introduce polar coordinates with the origin at f1. So for any point, this is a point psi eta, we'll have a radius vector r and the polar angle, which I will denote, let's say, by phi. In this case, you remember the relationship between the rectangular and polar coordinates. So we say psi is r cosine phi, eta is r sine phi. And therefore, substituting it all together, we get x is r cosine phi plus AE at, y is r sine phi. And now this is to be substituted into our original equation, which says that x squared over a squared plus y squared over b squared is 1. Therefore, we get r cosine phi plus AE squared divided by a squared plus r squared sine squared phi. For b squared, we'll be using exactly this formula, so we'll say a squared 1 minus e squared equals to 1. Or multiplying both sides by the denominator a squared 1 minus e squared, we get r cosine phi plus ae squared times 1 minus e squared plus r squared sine squared phi equals to a squared 1 minus e squared. Okay, so our objective is to find r as a function of phi, which would be exactly the ellipse equation in the polar coordinates. R is a function of phi. Okay, so expanding the left-hand side, we get, what do we get when we expand the left-hand side? Well, let's do that. We say r squared cosine squared phi 1 minus e squared plus 2 times ae 1 minus e squared r cosine phi. Okay. Plus a squared e squared 1 minus e squared plus r squared sine squared phi equals to a squared 1 minus e squared. Okay, what can we do here? You see there is a term r squared cosine squared phi here and r squared sine squared phi here. They obviously recombine into r squared. So we get r squared minus e squared r squared cosine squared phi plus this term is unchanged. And this term is moved into the right-hand side. In the right-hand side, we already have a squared minus e squared minus same term, but also multiplied by e squared. Therefore, it would effectively be a squared 1 minus e squared squared. Please have a look. Is it clear? What happens when this term is moved into the right-hand side? You factor out
Yeah.
e squared, yes, 1 minus e squared, and then you get 1 minus e squared again. Wonderful. So, r squared 1 minus e squared cosine squared phi plus 2 times ae 1 minus e squared r cosine phi. Let's move everything into the left-hand side, actually. Minus a squared 1 minus e squared squared equals to 0. So we got, unfortunately, a quadratic equation in R. If we would like to express R as a function of phi, then we have to solve a quadratic equation. There is no easier way, but this is not tremendously difficult either. So what I will do before that, you remember that we, in the last lecture, we introduced the notion of a so-called focal parameter P of the ellipse. So the focal parameter is precisely the distance from the focus to the orthogonal to the main axis point in the ellipse. So if this is our M point, then MF1 is P. You remember? This is called focal parameter. And simply from the original ellipse equation, from the original one, substituting OF1 for x, which is AE, we derived P equals to A1 minus E squared. You remember, we considered, compared this with B and found that P being A1 minus E squared is less than B, which is A square root of 1 minus E squared. You remember. So A1 minus E squared is the focal parameter P. So here we have P squared, and here A1 minus E squared is P as well, just for simplicity. So this equation can be rewritten as r squared 1 minus e squared cosine squared phi plus the eccentricity here is not in P, so it is 2e p r cosine phi minus p squared equals to 0. Solving this equation, we get two roots, r12, which is 1 divided by the leading coefficient, 1 minus e squared cosine squared phi. Now, please have a look that we assume the eccentricity being less than 1 and greater than equal to 0. And therefore, in this situation, the coefficient at r squared never vanishes. So this coefficient is always greater than 0 as a result. Okay? Because the absolute value of the value of cosine squared phi is at most 1, but e is less than 1. So 1 minus this term is always positive. Times minus ep cosine phi plus minus square root of e squared p squared cosine squared phi plus effectively the product of the first and the third term, p squared 1 minus e squared cosine squared phi. And from this you can immediately see that the discriminant is actually equal to p squared. So we can, as a result, say it is 1 divided by 1 minus e squared cosine squared phi minus ep cosine phi plus minus p. So this is p squared. E squared, p squared, cosine squared phi cancels. And therefore, we get p minus e cosine phi plus minus 1 divided by 1 minus e squared cosine squared phi. These are the roots. But obviously r, being the radius vector, must be positive. For the positive one, only the plus sign would do. Minus would immediately result in the negative, always negative numerator. So r equals to p 1 minus e cosine phi 1 minus e squared cosine squared phi. And because 1 minus e cosine phi, as we said, is never 0, it is actually always positive, then we can cancel this term in the numerator and denominator. Obviously, the denominator is 1 minus e cosine phi 1 plus r cosine phi, and we eventually get p divided by 1 plus e cosine phi. That's what we wanted. This is the formula we wanted. We'll need to remember it. It will be very much useful when we study Keplerian orbital motion. So obviously, if we look at our drawing, let's get back. The nearest point to the focus, which is called the pericenter, more correctly call it perifocus, but in fact it is a pericenter or perifocus. And the most distant point from the focus is called epicenter, or more correctly apofocus. So the pericenter distance is, this point corresponds to which value of phi? Which value of phi is here?
0.
Here phi is 0. And which phi is here in epicenter?
Pi.
Pi, indeed. So the pericenter is 0, epicenter is pi. Therefore, from this formula, it is very easy to compute the pericenter distance. Our pericenter distance it is conventionally denoted by Q, which is R of 0, so phi equals to 0 here, which is P over 1 plus E, but we also know that P is A 1 minus E squared over 1 plus P, 1 plus E, and therefore it is A 1 minus E. Epicenter distance conventionally denoted by Q capital, which is R of pi, which means that phi is pi here. Cosine of pi is minus 1, therefore it is P over 1 minus E, which is A 1 minus E squared over 1 minus E, which is A times 1 plus E. As we will see, this formula for Q as A1 minus E, it holds for the ellipse only, but the general formula that the pericenter distance is p over 1 plus e. It also holds for a parabola and a hyperbola as well. Okay, so that should be clear. There are many other interesting things we can discuss about the ellipse, but I think we got the general impression of how the geometry of the ellipse looks like. Any questions so far? If not yet, let us move into the next topic. We'll study the hyperbola. So let us recall the equation of the hyperbola. X squared over a squared, but now minus y squared over b squared equals to 1. This is considered to be the general equation for the hyperbola. A and b are parameters with a different geometrical meaning compared to the ellipse. Sometimes they are also called semi-major and semi-minor axes, but the geometrical meaning is quite different. So for the moment, let's keep them just as parameters. We'll see what they actually mean. Okay, now let's draw it up. With this equation, x is never 0, because if we substitute x equals to 0, then we would have minus y squared over b squared equals to 1, which cannot happen for any y. Therefore, the minimum value of x would be that corresponding to the second term being 0, which means that the minimum value of x is actually a. So if we, or minus a. So we would say x squared is greater than a in this case, because the second term is greater than or equal to 0. Okay, that's clear. X squared over a squared, which is 1 plus y squared over b squared. All right, therefore it is greater than or equal to 1 always, and that's why x squared is greater than or equal to a squared, or absolute value of absolute value of x is greater than or equal to a. We consider that a is positive. Okay, so then the graph of a hyperbola looks like this. And now we assume that both actually x and y tend to infinity. Say x squared and y squared tend to infinity. If they tend to infinity, then in this equation, for very large x and y, we can omit, drop, neglect the term 1, because it becomes small, infinitesimally small compared to y squared over b squared. So in that case, we can say that asymptotically x squared over a squared can be approximated as y squared over b squared, simply because both x and y are significantly greater than 1 in this case. Or we can say that y over x is approximately equal to y over x squared, let's say, b over a squared. But what is y over x? Y over x is the angle coefficient, the tangent of a straight line. So if we have y equals to some alpha x, then alpha is the tangent of this straight line, which means that for very large x and y, we really have this type of equation that y can be approximated as alpha x, where alpha is plus minus b over a. Okay, which means that asymptotically, as x and y tend to infinity, our hyperbola approaches indeed a straight line, which is called the asymptote of our hyperbola. So this line is indeed y equals to, assuming that both a and b are positive, so this straight line is y equals to b over a x, where the other branch of our hyperbola asymptotically approaches the line y equals to minus b over a x. And when we extend this line beyond 0 into negative x or y, then we have exactly same asymptotic properties for the other branches of our hyperbola. Okay? So, and this is the same line. You understand my hand drawing. So here is y equals to same line minus b over ax, and this is the same line y equals to plus b over ax. Okay, so what is the angle? Geometrically this means that for very, very, very large x and y, you can think that these branches of hyperbola becomes nearly straight. They asymptotically approach straight lines. So here, of course, it is a curve. It is a curvilinear second order trajectory, whereas as x and y tend to infinity, we have nearly straight line behavior for branches of our hyperbola. Nearly straight line. Okay? Something which we never get for the ellipse. Our hyperbola asymptotically approaches the straight line. What is the angle between those straight lines? So this is the angle. Let me denote it by, for example, beta. We can say that half of this angle is characterized by the property that tangent beta half is obviously equal to what?
B over A.
Yes, equals to alpha, which is b over a. And because both b and a are positive, we can say that this half angle is greater than 0. This is positive, and less than pi over 2, and therefore beta itself is greater than 0 and less than pi. So this altogether beta angle can of course become blunt one as well. So for example, something like this. Okay, fine. Or there is another possibility for a hyperbola. And then obviously we can say that beta is 2 times arctangent will be over A. Okay. Or there is another possibility, obviously, which is not a canonical equation, but we need to be aware of that, that the equation is written other way around. You may get that expression as well, that y squared over b squared minus x squared over a squared equals to 1. So basically other way around. Or if we keep it in the original form, x squared over a squared minus y squared over b squared would be minus 1. In this case, the geometric shape is different. So in this case, x equals to 0 is possible, but y equals to 0 is not possible. And therefore, we have a hyperbola like this, again with asymptotus, and therefore we have a similar branch here. So when we see an equation, always remember to check in which form it is written, like this or like the first one. Okay, but we also think whether we have, similar to the ellipse, possibly focal points in our hyperbola. And yes, indeed we do. So hyperbola, as well as the ellipse, has 240. Let us denote them by F1 and F2. Returning briefly to the ellipse, you remember that, as discussed previously, there is a second focus here, F2, and the distance from pericenter to the first focus and epicenter to the second focus, these both distances are the same and equal to q, okay? And you remember the focal property of the ellipse, that for each point, the sum of distances, f1 to the point plus point to, f2 to the point plus point to f1 is a constant and equal to 2 times a. You remember that. By the way, moreover, there is an interesting thing which you can prove for yourself in the following. So yes, if we take an arbitrary point here, and then we draw a tangential line to the ellipse, from your mathematical analysis course, you already know how to draw tangential lines, right? You get the derivative, and you get the slope of this tangential line using the derivative, right? Y over x. So what happens in that case is that if you do this tangential line, and then you also do a normal line, which is orthogonal to the tangential line. Okay, that's my hand drawing. Then the angles f1 to, suppose this is the point M, f1 to M, which is making with, let's say, a tangential or normal line. So for example, this is an angle, I don't know, alpha, would be equal to this angle, f2 to our M point, made with a tangential line. And obviously their complements, pi minus a to the normal, pi minus alpha, pi over 2 minus alpha, and pi over 2 minus alpha here to the normal are also equal. Which means that if we think that our ellipse is a kind of reflecting surface, and you put a light source in f1, then whatever point in the ellipse you get, a ray of light reaches the point M, and then it is reflected from the surface of the ellipse at the same angle alpha as it fell, and then it will get into the second focus. So if you have a light source here, then all light rays reflected by the ellipse will get into the second focus. That's why they are called foci, very much like optical focal points. In optics, they're really focal points, which means that if you put a bulb here, all light rays actually come together in F2, and if you put some flammable material here, then those light rays will ignite this flammable material put into F2. Because all energy from the light source in F1 comes into F2. That's an interesting property which you can prove by simply drawing up the equation for the tangential line and computing the angle of F1M with respect to this line and MF2 with respect to this line. You will see that the angles are equal, and therefore the fall angle equals to reflection angle, and therefore you have a full reflection into F2 from the optical point of view. Okay, so now for the hyperbola, there are also two focal points, but now the properties are different. Then for any point M in the hyperbola, if we construct distances F1M and F2M, what do you think, what kind of property would be holding in this case?
Maybe difference of the length.
You're absolutely right. It is indeed the case. So in this case, it would be F2M minus F1M, because I selected M in the left branch. Then obviously F2M is greater than F1M. So this difference is constant. And it is even easy to say what it is. Because if we put M here, then again the perifocal distance is between the pericenter and foci. Let us denote it as for the ellipse by Q. So it is Q and Q here. And from this point to this point, we already know that it is A. Because when y is 0, then x equals to plus minus A. We already got that. Okay? Therefore, what would it be in this case? If our point M is here, then F2M is Q plus A plus A. Once again, Q plus A plus A minus F1M in this case is Q. Therefore, it is equal to 2 times A. By the way, exactly same as for the ellipse, with the difference that it is now, yes, a difference rather than a sum. Okay. From this, we can introduce, so if this property holds, then we can really say that from this property we can derive indeed the equation of the ellipse, of the hyperbola, very much like we did for the ellipse, similar to the case of ellipse. And we get as a result that x squared over a squared plus, minus y squared over, it's interesting, over b squared is indeed 1, whereas you remember for the for the ellipse, we're interested in the distance, the coordinate between the center of our coordinate system and the 40. So it is OF1, same as OF2, obviously. You can denote it by, in our notation, it is A plus Q. And this distance, A plus Q, we can also denote it possibly as C. Then we can say that, obviously, which is greater than A, because Q is positive. And in this case, by just computing this equation from this property that the difference of distances is a constant one, you will actually get the relationship that b squared equals to c squared minus e squared. As c is greater than a, this is always the case. So it is a plus q squared minus a squared. So that's the relationship for the hyperbola. And for the hyperbola, we introduce the eccentricity as well. And the eccentricity of the hyperbola, you remember the eccentricity of the ellipse was the distance between the center and the focus divided by a, right?
Yeah.
So similar to ellipse, we introduce it in the same way. It is O F I, where I is 1 or 2, divided by a. But O F I is C. So it is C divided by A, or it is A plus Q divided by A, which is obviously greater than 1. So for the ellipse, the eccentricity is less than 1. For the hyperbola, the eccentricity is greater than 1. So you can rewrite the equation of the hyperbola as x squared over a squared minus y squared. For the b squared, it will you can write it as c squared minus a squared being equal to 1, or c squared minus e squared is obviously, if by definition c is ae, then c squared minus e squared equals to a squared e squared minus 1. So this is a squared e squared minus 1, from which it follows that for the hyperbola, b is a times square root of e squared minus 1. You remember that for the ellipse it was the other way around, 1 minus e squared. Now it is e squared minus 1 because the eccentricity is greater than 1. So we still have exactly, well, similar parameters a and b. They are not major and minor semi-axis in the elliptic form. because unlike the ellipse, the hyperbola is unbounded, all right? But you can still think that A is the distance between the center and the nearest hyperbola point. Q is the distance from focus to this nearest point. By the way, we can derive Q now. So what is Q? Q is, because C is A plus Q, therefore Q is C minus A. Once again, this is C, this is C, this is Q, this is A. C minus A, therefore it is AE minus A, and therefore it is A times E minus 1. Again, for the ellipse, it was A times 1 minus E, you remember. And obviously, unlike the ellipse, there is no Q capital, there is no epicenter, the largest distance between the focus and the hyperbolic point, simply because the hyperbola is unbounded. So let us maybe even do a summary of formulas. So ellipse. Eccentricity is from 0 to 1. We are not considering the degenerate case of rectilinear ellipse. You remember when we could say that E equals to 1. For the moment, it is a generic ellipse. Hyperbola. E is greater than 1. Equation of the ellipse is a squared over a squared plus y squared over b squared equals to 1. For the hyperbola, it is x squared over a squared minus y squared over b squared equals to 1. A bounded curve for finite size. Hyperbola is unbounded. We can say that Q is A times 1 minus C. Here Q is A times E minus 1. Here B equals to A square root of 1 minus C squared. Here B equals to A times square root of E squared minus 1. Okay, so what else? For the ellipse, we had a focal parameter. You remember the focal parameter, which was P was equal to A times 1 minus E squared. Very easily you can see that in a similar way, here the focal parameter will be A times E squared minus 1. Comparing these two equations, you can see that P equals to A1 plus E. Oh, sorry, Q times 1 plus E. If P is A1 minus E squared and Q is 1 minus E, therefore P is Q1 plus E. Here it is the same, actually, although P and Q by themselves are different equations. We have E minus 1, E squared minus 1 compared to 1 minus E squared, but nevertheless, it is still the case that P equals to Q times E plus 1, obviously, which is Q1 plus E. Let's see. The apofocal distance Q is, as we found it, A times 1 plus E in this case. And it would not be Q equals to A times 1 plus E here. Here Q equals to what? For the hyperbola? plus infinity. There is no maximum distance from the focus to the hyperbola. Hyperbola goes to infinity. That's why in astrodynamics it is called a hyperbolic escape trajectory, which allows a spacecraft, for example, to permanently leave the gravitational sphere of the Earth, or if it is a hyperbolic escape trajectory versus with respect to the Sun, like for example all those high-speed probes like Voyager, then it is a hyperbolic escape trajectory which allows the spacecraft to escape the solar system. Okay, so I hope this summary of formulas will be useful. Okay, any questions so far? Okay, we're okay with that. But now let's go back to just your school years. And you remember how the hyperbola was first introduced at school? We had the equation xy equals to constant, uh, and this was also a hyperbola. It was called a hyperbola, and it is only if we draw it up. Suppose that, for example, we're drawing up an equation xy equals to 1, the most simple. Then it is like this: xy, xy, and two branches of the hyperbola. So, looking into our original definition of the hyperbola, this is a different equation. How do you think we can obtain our definition of x squared over a squared minus y squared over b squared equals to 1 as well?
Maybe by rotation of axes.
Of course, by rotation. You're absolutely right. So in fact, it is all same as we have already seen, but only by rotation and maybe by some minor scaling. Let's see. So now if we put other coordinate axes, for example, x prime and y prime, orthogonal to each other, at the angle of precisely, let me call it alpha, which is pi over 4, compared to the original, then you can see that in this x prime and y prime, this would indeed be looking like our original hyperbola, with now the original axis OX or Y being asymptotes of the hyperbola. So let's do indeed this transformation. So we'll see the equation of our hyperbola in the new coordinates x prime and y prime. So because the angle is pi over 2, you remember for a two-dimensional rotation, old coordinates are expressed via the new ones in the following way: x equals to x prime cosine alpha minus y prime sine alpha, y equals to x prime sine alpha plus y prime cosine alpha. All right? Okay. And we have the equation xy equals to, in this case, 1. So let's substitute these expressions for x and y through the new coordinates x prime and y prime and see what happens. X prime cosine alpha minus y prime sine alpha times x prime sine alpha plus y prime cosine alpha equals to 1. But obviously for alpha being pi over 4, we have cosine alpha equals to sine alpha equals to 1 square root of 2 halved. Okay. Therefore, we can take out both actually cosine alpha, sine alpha, and cosine alpha, taking out of this equation. They are all equal in this particular case. Therefore, we have 1 over 2 x prime minus y prime x prime plus y prime equals to 1. Or this means that x prime squared minus y prime squared over 2 equals to 1. Or x prime, let us do it in this way. X prime squared divided by square root of 2 squared minus y prime squared divided by square root of 2 squared equals to 1. Therefore, A equals
Excuse
to
me,
B,
Professor.
yes, equals to square root of 2. Let's see if we did it correctly. Yes?
I think you lost square root of 2 in the equation.
Here, you see, cosine alpha is square root of 2 halved. So we extract a factor out, take square root of 2 halved from this first bracket and from the second bracket.
Oh, I see.
Therefore, it is 1/2 altogether. All right? This, 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 and this. Okay, that's why we got 1/2 in front. So yes, after rotation, we arrived at the same hyperbola as originally, well, as in our original equation, with A and B being equal and equal to the square root of 2. So let us, in that case, for that hyperbola, let us compute the eccentricity. We already know that B equals to A times square root of E squared minus 1. Okay? In this case, A equals to B. Therefore, square root of E squared minus 1 equals to 1. And therefore, E squared is 2. And therefore, the eccentricity is square root of 2. Not because A and B are equal to square root of 2. No. It is because A and B could be absolutely any. What is important is that A and B are equal. And if A and B are equal, this implies that the eccentricity is equal to square root of 2. And if we look at this picture, then somewhere here, we have 240. This is F1 of our hyperbola, and this is F2. So Again, this is A. This is A as well. And we now know that A is square root of 2. All right. This is Q. Q in this case equals to, if you remember, A times E minus 1. A is square root of 2. E is square root of 2 as well. Therefore, it is 2 minus square root of 2. So that's Q. This distance is Q. This is A. And altogether, C, which is altogether or F1 or F2 or Fi, which is A plus Q, which is obviously the eccentricity is, you remember, it is C over A, therefore C is AE, which is similar actually to the ellipse. And therefore A square root of 2 is also square root of 2, therefore this distance is precisely 2. Okay. So that's about this particular case of a hyperbola. And now one can wonder, so indeed, we considered the canonical equations for the ellipse and hyperbola, but there are many other ways of how these equations can be expressed. So first of all, what about the hyperbola in the polar coordinates? For the ellipse, we got already its equation in the polar coordinates. By the way, we can also say that here if we define for the ellipse C is being the distance OF1, nearest focus, yes, actually for any focus, OFI, then this is AE, and here C is OFI being AE as well, but only for the ellipse bounded and O is inside the ellipse, the origin, right? And hyperbola is unbounded and O is outside the hyperbola. Okay, for the ellipse and polar coordinates, by the way, for the ellipse and polar coordinates, we had again r equals to p over 1 plus e cosine phi. Interestingly enough, for the hyperbola, it will be exactly same. We can obtain this equation for the hyperbola exactly in the same way as we did for the ellipse by translating our origin into the focus and then introducing polar coordinates. So we'll get exactly same equation, but obviously with different values of E. For the ellipse, E is less than 1. For the hyperbola, E is greater than 1. The focal parameter P is defined for both actually equation for both ellipse and hyperbola. For hyperbola, our focal parameter is this. If we take the focus and draw up the orthogonal line to the main axis, So that's P. And a similar thing for the second focus. That's P. And then we get exactly same equations in the polar coordinates. So for example, if now I'm talking about the left branch, so for F1, we introduce R and phi and phi, radius vector and the polar angle, R and phi, then it would be exactly same equation, R equals to P, where P is this focal parameter, 1 plus E cosine phi. Exactly same story. But now for the hyperbola, let us look a little bit more carefully at this equation. One second. I'm moving my drawing. Okay. So hyperbola in polar coordinates. Remember, origin is not O in this case. Origin is F1. R of phi equals to exactly same as for the ellipse, P over 1 plus E cosine phi. But now E is greater than 1, which means that the denominator may vanish and will vanish. So the denominator is no longer bounded away from 0. So for example, when phi equals to 0, this means that R equals to P over 1 plus E, and because P is, in this case, A E squared minus 1 over 1 plus E, which is A E minus 1, which is Q indeed, as we have already seen. So that's correct. Now let's say phi increases. When phi increases, cosine phi obviously decreases, and eventually the denominator decreases. And eventually phi equals to the maximum possible value of phi. The denominator becomes 0. And that's all. So phi cannot be greater than this phi max. So let us find the value of this phi max. What do you think actually this phi max geometrically? Let's have a look at our drawing of the hyperbola. Let us ask the question actually what the phi max is. So that's our phi, right? I'm looking at the left branch of the hyperbola. So phi is 0, we are here. Now phi increases, 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 but as we see from that equation in the polar coordinates, that phi cannot be greater than a certain phi max, because then the denom vanishes. So what do you think is the maximum value of phi? You see that the inclination, the slope angle for the asymptote is this half beta, which we have already defined. You remember that the tangent of half beta, which is equal to, in this case, b over a. So my argument is that phi, although you see the angle between asymptotes is centered in the origin O. Phi, this angle, is with the apex in the point F1. But when phi increases and becomes large, the corresponding radius vector would become effectively parallel to the asymptote. And this really means that our hyperbola goes to infinity. That F1 is not the same as O doesn't matter in this case, because when the radius vector becomes larger and larger and larger, the difference in the basis between phi F1 and O becomes insignificant. So I can argue that perhaps phi max is simply vector over 2, which is arctangent of B over A. Let's check that. That's very easy to see. Obviously, phi max corresponds to the condition. Geometrically, it is arctangent of B over A. Geometrically. Oh my god, sorry. Moving a large picture becomes more and more difficult. My computer is not powerful enough to do it. Okay. Phi max corresponds to the denominator being equal to 0, and therefore 1 plus e cosine phi max is 0. Therefore cosine phi max is what? Minus 1 divided by e. Okay? Minus 1 divided by e. Okay. Cosine squared of phi max is 1 divided by e squared. Now we have the equation that tangent square of any, let's say, alpha plus 1 equals to 1 over cosine squared of alpha. Therefore, 1 over cosine squared of phi max is e squared. Then tangent squared of phi max is e squared minus 1. But what is e squared minus 1? We had the equation that b was a square root of e squared minus 1 for the hyperbola. Therefore, e squared minus 1 is nothing but b squared over a squared. So e squared minus 1 is indeed b squared over a squared. From this it follows that tangent of phi max, which we assume to be positive, is indeed b over a, which is the same as tangent of beta half, and therefore phi max is indeed beta half. So that's what we actually could have seen from the geometric considerations. The maximum polar angle of the hyperbola is half angle between the asymptotic branches. Okay, that's a reasonable value. Okay, so we got what we wanted. Unfortunately or fortunately, the polar angle of the hyperbola cannot go to pi in general. There is a limit, and this limit is less than pi, and that corresponds to the half angle between the branches of the hyperbola. Okay. Now, any questions about this? If no questions about this, we move into our final topic. General form, general and canonical form of second order curves. The general form of second order curves is the general second order equation in xy, which we write in the following way. You will see my notation: a11 x squared. Why a11? It is some kind of coefficient a at x multiplied by x. So we say x is the first coordinate, y is the second coordinate. Therefore, a coefficient at x is a11 plus a12 xy. It is a coefficient at the product of the first and the second coordinate, plus a22 y squared plus, how would we call the coefficient at x itself, the linear term? What do you think from this notation?
A1.
A1, you are right, a1x plus a2y. There is also a free term. How would we call the free term in this case?
A.
All of them have indices. If it is
A0.
A0, of course. A0. And because the free term is arbitrary, we can put 0 in the right-hand side. So let's consider the general equation of this form. So we assume that not all of a11, a12, a22, these are quadratic coefficients. Quadratic coefficients. Not all of them are 0. Okay? Because if all of them are 0, then we have just a linear equation. A1x plus a2y plus a0 being equal to 0. Then it is not interesting. All right? So not the whole quadratic part is 0. Okay. In this general formulation, if you are given an equation like this, it is actually one of our curves we have already studied. It is an ellipse, a parabola, a hyperbola, maybe a circle, maybe a degenerate case of, let's say, a pair of straight lines, but from the equation itself, it is not clear what it is. So we need to transform this general form into a canonical form to get equations similar to what we had for the ellipse, parabola, and hyperbola. Canonical means simple form. And in doing that, determine, first of all, the shape, and then also the orientation of the original second order curves in the original coordinates. By the way, we have already seen that in polar coordinates, our equation, once again, are being p over 1 plus e cosine phi. An intermediate remark. It also holds for a parabola. For the parabola, the eccentricity is 1. And because the eccentricity is 1, phi max is actually, for the hyperbola, phi is greater than or equal to 0 and less than phi max. Phi max is not reached. For a parabola, it is the same thing. Phi max is pi, and therefore phi is greater than or equal greater than or equal to 0 and less than pi. So only phi equals to pi is excluded, because if phi equals to pi and e equals to 1, we have r being focal parameter over 1 plus cosine phi, and therefore cosine phi must not be equal to -1. Therefore phi equals to pi is excluded. Same equation. Once again, it is a very, very, very important one in polar coordinates. As we have seen, it stands for actually both ellipse, parabola, and hyperbola. And actually it stands for a circle as well, because for the circle, E is 0, and then R is a constant, equals to the focal parameter P. So it is applicable to all cases. In the rectangular coordinates, x and y, it is a more difficult situation because we really need to transform this equation to see what is the shape of our curve. May I ask you, in your practical sessions, have you already been doing that? General and canonical form of second order curves and transformation to the canonical form? Not yet?
We did such thing with ellipse on tutorial.
You did it with the ellipse in tutorials, but not with the parabola. Okay.
Yeah.
And probably what you may or may have also been doing, did it include the most general cases when we have this cross term xy, a12xy? Okay, so transformation to the canonical form in general, so we don't know whether it is an ellipse or parabola or hyperbola. It first, step 1, would always be eliminate xy if a12 is non-zero. If a12 is 0, then you already have a nearly canonical form for the quadratic part. You have a11x squared plus a22y squared, where they can be of same sign, of different sign, and so on. But if xy is not equal to 0, then we need to eliminate xy first. How do we eliminate xy? By suitable rotation. By suitable rotation. At angle alpha. We don't know yet what alpha is in this case, so we introduce a general rotation. So new coordinates x prime, y prime, such that old coordinates x, y, again, it is x prime cosine alpha minus y prime sine alpha. Y is x prime sine alpha plus y prime cosine alpha. Again, always check that the determinant of this transformation, cosine squared alpha plus sine squared alpha, is obviously equal to 1 because it is a rotation in all cases, as we have already discussed. Substituting this x and y into the original equation, we then get a11 x prime cosine alpha minus y prime sine alpha squared plus a12 x prime cosine alpha minus y prime sine alpha x prime sine alpha plus y prime cosine alpha plus a22 y squared, which is x prime sine alpha plus y prime cosine alpha squared plus linear and constant terms, which we are not interested in yet because our objective is to eliminate the cross product at the moment, equals to 0. Then expanding, at the moment you can expand the quadratic terms only, and let us collect the terms at new coefficients x prime, at new coefficients x prime squared, y prime squared, and the cross term x prime, y prime. So what do we get? For the coefficient at x prime squared is multiplied by what? A11 cosine squared alpha, and that's all from the first bracket. From the second bracket, it is plus